Hi, my name is Gupta Khan. In this video, we are going to look at the phase relationship between voltage across a resistor and a voltage across a capacitor when a resistor and capacitors are connected in series in an AC circuit. So this is an AC supply, a switch, a resistor, and a capacitor. And let's bring it to real one. Let's turn the switch on. So this is the current time graph. So it's measuring the current, and current is same everywhere in a series circuit. Now this voltage time graph is across the resistor. So it's measuring the voltage across the resistor at different times. And this one is measuring the voltage or recording the voltage at different times across the capacitor. So let's compare first of all, what is the phase relationship between the current and the voltage across the resistor. Now, if you look at this trace over here, so at this particular time, current is almost maximum, and the voltage across the resistor is maximum. Or we can say that current and voltage across the resistor, they are in phase. They become maximum at the same time, and then they become minimum at the same time. Let's look at. So now the current has became negative maximum. It just started increasing in a negative manner. And then the voltage is also had reached its maximum, and it is becoming a little bit less negative. And again, if we look at then current and voltage across the resistor, they are in phase because they're becoming negative maximum and positive maximum at the same time. Now we will compare the voltage across the resistor and the voltage across the capacitor. So let's just stop it. As you can see from here, voltage across the resistor has reached its maximum, whereas over here, it is a little bit less than voltage. Voltage across the capacitor hasn't reached its maximum values. It will reach its maximum value after a quarter of a period, or we can say that voltage across the capacitor is quarter of a cycle behind the voltage across the resistor. We will just look at one more value. I will turn it on. Now, if we look over here, the voltage across the resistor at this particular time is almost zero, whereas the voltage across the capacitor is negative maximum. It still has to reach zero. So after a quarter of cycle, it will reach zero. Or in other words, what we can say is that voltage across the capacitor is 90 degrees behind the voltage across the resistor. Now let's look at some notes for this topic. So what we can, so these are the graphs. So this is the current time graph. That's the voltage across the resistor, and they are in phase. They're becoming maximum and zero and minimum together. This, the green graph, is the voltage across the resistor. So when voltage across the resistor is zero, this one is a negative maximum, and it becomes zero after a quarter of a cycle. So that is one full period. So that's a quarter of a cycle. Or what we can say is that voltage across the resistor and current, they are in phase, whereas voltage across the capacitor lags. Sorry, that's a major mistake here. Lags VR by 90 degrees. I will make the correction later. Now, if we want to calculate now what will be the supply voltage, so over here, AC supply or AC battery or AC generator is supplying voltage. Capacitor and resistor are sharing the voltage. But if this one is, say, for example, 4 volts and this one is 3 volts, so we cannot say that this will be, we cannot add them in a scalar manner. We will have to add them in a vector manner because they are not in phase. And how we will add those voltages, we will have to draw phasors or vectors. So that's, and conventionally, voltage across the resistor is drawn over here, voltage across the capacitor is drawn over here, and so that is the vector sum of these two. So that's the voltage across the battery or voltage across the supply. So we add them, V supply square is VC square plus VR square, and then current is always in phase with the voltage across the resistors. If we draw a current phasor, that will be along here. So supply voltage or the battery voltage is behind the current by these many degrees. And how do we find this angle? What we are saying is V supply lags the current by this many degrees. And how do we use that? We find the tan theta, opposite over adjacent, and that gives us the angle, so we can calculate that one. Now, because voltage and across the capacitor and voltage across the resistor, they're not in phase. So when we want to find the total impedance of the capacitor resistor circuit, we will have to draw them like vectors again. So impedance is the total reactance of the capacitor and resistor circuit, and it changes with the frequency. So we add them like vectors, or total impedance of capacitor resistor circuit is R square plus XC square. And then again, the angle or the angle between the total voltage or total impedance and the current will be same. We find the tan theta, and tan theta will be XC, opposite over adjacent. So that was all about the notes in this topic. When we want to solve these capacitor resistor circuit problems, I've just written some guidelines here. So first of all, if we are given the capacitance of the capacitor, we calculate the reactance of the capacitor by using that formula, 1 over 2 pi fc. F is the frequency, C is the capacitance. Then we find the total impedance by impedance square equals R square plus XC square. And then we find the total current in the circuit, and total current in the circuit is total voltage, that's the voltage of the supply, divided by the total impedance, that will give you the total current. And then to calculate the voltage across the capacitor, we use the formula V capacitor equals I times XC, that's the reactance of the capacitor, and VR voltage across the resistor is I times R. So thank you, that's all for this video.